Hello everyone. Today in this video we are going to discuss how our multiplexer or a MUX can be used as a function generator. So let us study this with the help of an example. The question says implement the function y of a, b, c, d, which is defined by the mean terms 1, 2, 3, 4, 5, 12, 13, 14 and 15 using a suitable MUX. Now it is a 4 variable question, that is a, b, c and d, and they have asked us to use any suitable MUX. So we can use any MUX of our choice. We can use a 16:1 MUX. You can even use an 8:1 MUX. But here what we are going to see is the implementation using 4:1 MUX. So let's see. Here is the question. So let us have a 4:1 MUX first. 4 inputs, that is I0, I1, I2 and I3. 2 select lines S1 and S0 and 1 output Y. Now we can either opt for the K-map method or we can go by the truth table method. Both will lead you to the same answer. So here we are going to see the truth table method. So let us have the truth table. It has the 4 inputs, that is A, B, C and D, and 1 output Y, and Y is defined as logic 1 for all the given mean terms in the question and 0 otherwise. Now in such a question, what do we do is we apply the inputs to the select lines, right? So here we have 4 inputs, that is A, B, C and D, and 2 select lines S1 and S0. So out of the 4 available inputs, we can connect only 2 inputs to the select lines. So we'll connect the MSB of the inputs, that is A and B, to the select lines S1 and S0. So A goes to S1 and B goes to S0. So now that we are done with A and B, what we are left with is C and D, and hence our area of focus becomes the variable C and D along with the output Y. Now what we need to see is how Y varies as a function of C and D. So to make things easier, we'll further divide this into 4 groups. The first group, that is the first 4 combinations, it has A and B, they both equal to 0. The next 4 combinations, it has A equal to 0, B equal to 1. The next 4, A equal to 1, B equal to 0. And the last 4, A is also 1 and B is also 1. Now for each group we have to see how Y varies as a function of C and D. So if I talk about the first group, I can see Y is 0, 111. So if you can just recall, this is nothing but similar to the truth table of an OR gate, wherein your output is 0 when both the inputs are 0 and 1 even if one of the inputs is 1. So I can say that in this case Y is nothing but C ORing with D. So I can define Y is equal to C or D. Similarly, next case, Y is 1100. Now this doesn't remind me of any truth table of any of the gates, but if I observe it closely, I can see that these values of Y are completely inverted to what we have with C. So here I can say that Y is an inversion of C, or Y is equal to naught of C, right? Now the next 4 combinations, Y is 0, 0, 0, 0. That means irrespective of the values on C and D, Y continues to remain 0. So in such a case, I can say that Y is logic 0 throughout, right? Now the last case, Y is continuously 1 irrespective of the combination of C and D. In such a case, Y is nothing but completely logic 1. Now if this is done, I need to keep in mind the working of 4:1 MUX. I know that the 4 is to 1 MUX works on the basis of the combinations you have on the select lines. So here I know that S1 is nothing but A, S0 is nothing but B. So according to the truth table of a 4 is to 1 MUX, when both the select lines are 0, 0, what goes to the output is I0, right? So your Y becomes I0 when both A and B are 0, 0. So this can be seen in the first group, because in the first group we have A and B, they both equal to 0. So in that first group, Y is C ordering with D. So I can say that that is also equal to I0, right? Similarly, when A is equal to 0 and B is equal to 1, Y is nothing but equal to I1. And when A is 0 and B is 1, I know that Y is not of C. So that not of C is also equal to I1. Similarly, next combination, A is equal to 1, B is equal to 0, the output Y is I2, and for that case output Y is logic 0, which in turn will be equal to I2. Likewise, for the last case, when both A and B are 1, the output has to be I3, and in that case, from the given truth table, I have inferred that output will be logic 1, and that will be equal to I3. Right, now I've got the values of I0, I1, I2 and I3. I just need to make the connections. That is, C plus D will go to I0, C bar will go to I1, logic 0 will go to I2, and I3 will be fed with logic 1. And not to forget, mention the output Y of ABCD. So after these connections, I can now say that this function, which is defined by the mean terms 1, 2, 3, 4, 5, 12, 13, 14 and 15, has been successfully implemented with the help of a 4 is to 1 MUX. However, additional gates will be required in this case. Thank you.